Bismillah ar-Rahman ar-Rahim. So we stopped here last time. We talked about the main problem for the sensor node architecture is the concept of idle listening. The fact that the node spends a very long time listening to wireless signals without probably receiving any actual data on the wireless transceiver, which consumes energy for no reason. So we said that we would like to have a special mechanism for waking up the receiver through the wireless signal, but that's not actually built yet as of nowadays. So in terms of the sensor, so we discussed the communication part, the transceiver, how we can optimize the performance of the transceiver. On the other side, the sensor itself has different types. So we can classify the sensor types into active sensors versus passive sensors. So passive sensors, they tend to measure something passively from the environment, like pressure, like temperature, things like that. But the sensor does not send something to the environment. In other words, it does not send any energy or something like. For example, sending ultrasound. This is some type of active sensor. Sensing like radar signals, sending anything to the environment. This is some type of active sensing. So you send something, and then through the received signal, you can do your measurements. Okay, this is active sensing. This is active sensing. So when you send something to the environment, this is active sensing. If you don't send something, but you just like read light intensity, you read temperature, you read pressure, but without sending anything to the environment, this is called a passive sensing or passive sensor.
And why we need the passive sensing?
90% of the sensors are passive.
Oh, I think that if sensor does not react, for example, sense signal, sense anything, why it just sense?
Again, you're confusing the concept of sensing as sensing for communication. Here we're talking about sensing something, doing measurements from capturing the environment characteristics on the sensor side, not on the communication side. Sensing on the communication side is to detect whether there is a wireless signal or not. That's a totally different concept. Here we're talking about sensing, like capturing environment characteristics. I want to measure temperature. I want to measure pressure. I want to measure, like for example, the distance. I want to measure, I don't know, like corrosion on something like that.
Operators, for example, the operators came and take the results.
Operators, no. There's no operators in that case. We want to automatically capture some environment characteristics, and then collect some measurements, and then send it through communication, through wireless communication. So as we have discussed before, the sensor architecture. So we have the microcontroller in the middle, and here we have some wireless communication, and on this side we have some sensors, which could be, for example, a camera. It could be any type of sensing device. Okay, so the sensor interacts with the environment, whether on active basis or passive. Okay.
How active though?
Active, you send something. For example, you send some electromagnetic wave, and then through the received signal, you can do your measurement. You want to measure, for example, the distance, or you want to measure the location.
Like radar, yeah.
Yeah, like radar, or you send light. You send light, and then through the reflected light, you can detect, for example, distance, or you can Okay, so once you send something to the environment with the purpose of measurements, not with the purpose of communication, huh? Then this is some type of active sensor. Okay, so the microcontroller will then sample the signal measured, and then it will use the communication to communicate this information. Okay, so first we sense, and then we communicate.
It does not react with the environment. Just take the information. And
Right, so the passive one, the passive sensor, does not interact with the environment in the sense that it does not send something to the environment and receive something back.
Yes.
Okay, so this is passive sensor. Active sensor sends anything to them, whether it's light, whether it's ultrasound, whether electromagnetic wave, like magnetometers, for example. They send some kind of magnetic waves to the environment, and then through that it can detect whether, for example, there is a corrosion on a pipeline, or it can measure the depth, something like that. Okay. واضح الفرق؟ Okay. So another way of categorizing the sensor is whether it's directional or omnidirectional. And again, do not confuse this with the communication. Huh? Here, the sensor can be limited in terms of direction or angle, like camera. Okay, a camera is an example of a sensor, a passive sensor, right? Because it does not send anything to the environment.
Yes.
And it's directive, okay, in the sense that it has a limited field of view, right?
Yes.
Versus omnidirectional, like any type of pressure sensor or temperature sensor. It doesn't matter what is the direction or the orientation of the sensor is, right? So you can measure the temperature in the region, but it doesn't matter whether you are in this direction or this direction or that direction, right?
Yes.
So this is another way of categorizing the sensors. So examples, passive omnidirectional, examples like light sensors, thermometers, or microphones. These are passive in the sense that they do not send anything to the environment, and they are not, and they are omnidirectional, or they are agnostic to the direction, because it does not depend on the orientation of the sensor board to take certain measurements. Passive narrow beam or directive is the camera, of course. Active sensor is like a radar. A radar is some type of active sensor. So these two categories, or these two examples, are passive, one directional and one omnidirectional, and this is one example of an active sensor. Okay. An important parameter for that, especially for directive sensors here, is the area of coverage, and even for omnidirectional as well, because if you measure temperature like 5 or 10 meters far, then you're not measuring the temperature of that particular location. You're measuring the temperature of a location which is 5 meters apart from that, right? So in that case, again, although it has some analogy with the communication and things like that, but here the concepts are different. You can have some area coverage. So area coverage is actually a separate research problem on its own, even apart from communication. Okay, so I want to measure some characteristics from the environment, from this particular area. How can I deploy my sensors in such a way that allows me to measure the characteristics that I want from that environment? That requires, first of all, some kind of area coverage, because I want to measure, for example, the temperature in a certain area. I want to measure the temperature in this room and in that room and so on. So I want to deploy the sensors with the temperature sensors in each of these rooms. So this is a simple area coverage. However, in for example in an oil and gas site, this is like a huge area. Okay, and I want to, for example, make sure that I want to measure, for example, the health or the structure of a bridge or the structure of a pipeline. This pipeline goes, in different locations, and it can be as long as you can imagine, right? So I need to deploy my cameras. Okay, I need to deploy the cameras in such a way that allows me to cover all the key areas, right? Because of the limited view of the camera, I need to make sure that the camera is in particular location and it's pointed in a specific direction, which will allow me to cover certain area. But then another camera could be in another direction, in another location to cover. So by deploying these cameras in this location with these orientations, I can have a 100% coverage of this area. That's an area of research on its own. Okay, particularly if you're talking about the fact that whether the camera itself is moving or whether what you are measuring is actually moving. Because you can, for example, sense or cover, you want to cover, for example, some cars, whether there is some cars moving or not, or you want to check certain cars in a specific location. Okay, so this way the target is moving, and you want to cover this using cameras. So you want to make sure that wherever the car is moving, the camera will be covering that car. So now the car is moving, but the camera is fixed. It could be the other way around. Could be that you want to measure a bridge, or you want to monitor a structure of a bridge or a structure of a pipeline, but your camera could be moving. Like you can use that using mobile robots, you can use that using flying drones and things like that. So you could have mobile, fixed, mobile, fixed, something like that. So all these combinations are there. So the concept of coverage is a separate area of research on its own. And it's a very challenging area. So depending on the type of sensors that you are using, coverage could be very, very challenging. And you can have all types of techniques, whether it's optimization techniques, game theoretic techniques, and all of this you can apply it just on coverage, apart from communication. Okay, so sensor itself, this will be recorded. So sensor will also consume energy. So one of the things is that that we can use to reduce or to make the sensors energy efficient is to use what we call energy scavenging. And we talked about this topic before. And here we mention some specific examples for energy scavenging. So a laptop can be plugged in the wall and can get power from outlets, from outlet sockets. It's not a problem. A sensor node on the other side cannot do that. A sensor in many applications, the sensor node cannot be hooked up to the wall or cannot take energy directly from the power. Of course, for some applications it could, but in many applications this is very prohibitive. For example, if you want to deploy 1,000 sensors in a surveillance area, okay, it's very hard to have outlet powers in all these areas, right? So sensors need to be battery operated. So they can use batteries, of course, but the batteries are limited. So what we could do is that we can use other sources of energy, and these sources of energy are usually variable, and they are not that stable, like the power from the outlets or from the grid, right? Usually power from the grid is consistent. You can draw whatever current you want, and the power that you can get is consistent, and energy is infinity, because theoretically speaking, you can draw whatever energy you want from the outlet powers. However, these scavenging sources, these are limited in terms of the amount of power you can draw from them, and this limitation is actually, it may actually change from time to time, right? So for example, solar cells. Solar cells, you can draw between 10 microwatt to 15 milliwatt per centimeter. And by centimeter here, centimeter square, we mean the area of the cell itself, right?
It's the same as energy harvesting, or it's different?
Yeah, it's energy harvesting, yeah. So energy scavenging is energy harvesting, okay? So the range is actually very large. And that depends on so many things. It depends on the amount of light, whether there's sun, there's no sun, whether there is dirt on the solar cell itself. If there is some dirt on the solar cell, sometimes it affects the efficiency. So it depends on so many things. This range is very large. So the amount of power that you can draw from the solar cells is not as consistent as the outlet power. So if you, on one hand, we need to leverage energy scavenging or harvesting. We need to harvest energy, but we need to take that into consideration when we design the sensor, because the sensor that uses this type of energy needs to be tolerant in terms of the amount of power that it draws from the solar cells. Okay, and that's another interesting area of research, is that you have to make sure that the amount of energy you are consuming, okay, is less than or equal to the amount of energy you are harvesting, right? Since the amount of energy you're harvesting is variable with time, you need to sometimes use some prediction techniques. Okay, so you need to have some statistics on the amount of energy that you get every now and then, and predict, you know, the amount of energy that you will receive during a specific duration of time, and plan your energy consumption based on that. That affects both the sensing frequency, okay, and the communication. The communication protocol needs to be aware of this. The sensing needs to be aware of this, right? So you need to change everything based on the type of energy that you are harvesting. Examples are solar cells, temperature gradient. So any change or any gradient in temperature, even like this is 5 Kelvin. 5 Kelvin can produce a temperature of about 80 microwatt per centimeters. So if you have an area, okay, a square area, two-dimensional area, with a specific temperature, and this temperature changes, then you radiate some energy which corresponds to 80 microwatt per centimeter. Of course, if you want more power, in that case, you need to increase the area, right? So, if you have 2 centimeters, then that gives you 160 microwatts. So probably to have a decent amount of power here, by changing the temperature by about 5 Kelvin, you probably need an area of maybe, I don't know, like at least like 100 centimeters square or something like that, which is pretty big area, because the typical power in a sensor node for active sensing and communication is not less than 1 milliwatt. So you probably need maybe 10 centimeters or something at least to have a sensor working, 10 centimeters square. Vibration, this is the example of vibration. So you have a sensor, although it doesn't look clear here. You have a sensor here, this is a sensor board, on a machine which vibrates, right? And the sensor is supposed to measure the health of that machine. But the machine is actually giving the sensor the energy that it needs. So the machine is vibrating, and the sensor is actually harvesting energy from the vibration, and the sensor is actually measuring the health of the machine and communicating that to the sync node. So in a way, this looks like this situation here. So if you have this small fish that eats all the dirt from the shark, and the shark is actually feeding the fish and the fish, so it's a win-win situation here. So a vibration can draw anything between 0.1 to like 10,000 microwatt per centimeter cube. Of course, you don't have to memorize all these numbers. These are just numbers for your information. But the main thing here is that this range is huge, as you can see, and it depends on so many things. It depends on how the vibrations is happening. A good example of this is that you can set up these sensors on a bridge to measure, for example, the structural health of the bridge. Okay? So the bridge is actually vibrating because there are some cars passing over the bridge, right? So you can use these vibrations to power the sensors, and the sensors can then be used to measure the health of the bridge. Okay, so pressure variation, and pressure variation, by pressure variation we mean like if you have like a shoe, like you've probably seen that many times before. You have a shoe, whenever you step on the ground it just lights, right? So I mean, have you ever asked yourself, how does it light? Doesn't have any battery inside, so how does it do that? And that's actually what it uses. It uses some kind of piece of electric, like some pressure variation. Through the pressure variation, you can draw certain energy, which is enough to light some LED inside the shoe or something like this. And so of course, I mean, for a small purpose like lighting a LED or something like it's okay. But of course, the sensor needs a lot more than that. So probably pressure variation, what can feed like a small LED is probably not enough to power a sensor with a microcontroller, with communication transceiver, with sensor, and so on and so forth. So you need specific pressure variation to power a full sensor. So there is the micro electromechanical gas turbines. It's like these are micro gas turbines which are used, which use the airflow to draw energy. So we all know the big wind turbines, right? So when the air comes, it actually rotates the micro electromechanical is some kind of very minute copy of this big turbines in a small area, and it still uses the airflow to draw energy. These are some examples of energy harvesting that the sensor can use.
And is it enough to power the sensors? Because it's
you can have
brilliant.
MEMS are very commonly used. You can have actually you can have hundreds of these, because these are micro These are very small. So you can have many of these at the same time to power a sensor.
Yes, I know. I forgot the place, but one place that when worker are wearing some special shoes
Mm-hmm.
in the workspace.
Mm-hmm.
When they are moving, they are extracting energy from worker.
From?
These shoes when it is.
This is, you're talking about the piezoelectric one, not the MEMS, right? You're talking about the piezoelectric, the pressure
Yes,
variation,
yes.
right? Right.
Extracting energy
From the shoes
yes,
itself.
worker when they are going and coming.
Right.
They're extracting energy.
Right, right.
I always wonder if it is dangerous for people. It is safe or not. They're wearing some special shoes. It is safe or not for their health.
Well, this has nothing to do with the.
I'm
Yeah,
just-
but I don't think it's harmful because it's because again it's not you are not radiating anything to the environment, or you're not actually introducing anything aggressive to the environment, whether the person who's wearing it or whether the environment. So this is some type of passive way to draw energy. So through the pressure variation, which is happening anyway. So you just connect a small LED to use this energy to light the grid, because otherwise this energy transfers to the ground. This energy goes to the ground and it's not used.
There is
So
always energy in.
yeah, of course,
Oh,
this is Newton law.
I thought that because they are wearing these shoes.
Newton law. So it's energy. It always gets transformed from one form to another.
I thought because they are wearing these shoes, they have energy, not because.
No.
They always
You
have
they have to do some. They have to produce some pressure variation in order to generate this energy. Anyway, so as a very simple example, as a very rough estimation, of course, it's not accurate in any way. But just imagine that we have like the CPU or the processing unit of the microcontroller consumes about 1 nanojoule for each instruction. Of course, this is a very rough estimate. A small battery, like in a smart dust, can have a capacity of 1 joule, which means that you can execute up to 1 billion instructions before you have to recharge. Okay, so you're using this battery, you can execute up to 10 to the power 9 instructions before you have to recharge the battery. And we're talking about executing instructions, not the number of instructions or number of lines of code in the sensor, of course. So a small loop, if you are executing that 100 times, then this means you have 100 times the number of instructions for one single iteration. So in other words, this number, as huge as it might look, but it's not actually that big. And to understand this even better, if we can talk about a lifetime scenario, a single day of operation requires this number of seconds. So you have 24 hours times times 60 minutes times 60 seconds. You have this number of seconds. So if we assume 1 joule means that we have 11.5 microwatt as a consistent energy that can be extracted from the sensor board consistently for one single day. يعني to keep the sensor operating for one full day continuously. Okay, this is the amount of power you can draw. أعمل كده. لسه بفكر أبوظ الريكوردينج.
She told me there was an accident.
Okay. Okay, so so of course we don't have the typical value of the power that can keep the sensor operation, but I can tell you that this is way below that threshold. So this number is way below the threshold that you can keep the sensor board operating, even in idle listening mode, let alone active mode or sending or transmission mode. Okay, so this amount of power is really, really low, which means that it's not even feasible to keep the sensor board fed with power for one single day. Okay, because the amount of power that you can get is very low, and you cannot sustain the sensor node to keep it operational both on the sensing part as well as the communicating part.
That's why I asked you, it is enough to power the sensor.
Right, but remember that the harvesting part is renewable, which means that the battery has certain capacity and that's it. But the harvesting part is renewable energy, right? So whether it's enough or not, that's another story. I mean, you have to anticipate the amount of energy that you will get through a certain duration of time. In all cases, it's not enough to rely on the battery only and keep the sensor operating all the time. I mean, this is the main motivation why we need some optimization techniques, okay, to keep the sensor and the communication part, both, okay, utilized in a very extremely efficient way. Whatever you don't need at this point in time, you need to turn off or keep it sleeping in a very deep sleep mode, and only start it or wake it up whenever you need to actually utilize it.
Please, why 60?
60 minutes. 60 minutes, and the other one is 60 seconds. So the way out, we cannot afford running the sensor for operational mode, for full operation all the time. We cannot afford that. So so if there is nothing to do, you have to keep the sensor in a power save mode. But again, the question is how to wake it up. Okay, how and when to wake it up. Okay. So some controller modes. So as a typical mode in the controller itself, and by controller we mean the microcontroller, the processing unit. It can be in active, idle mode, or sleep mode. Okay, it cannot be in turned off mode, because turned off means that the whole board is, because this is the brain of the system. The brain cannot be dead. The brain can be in a sleep mode, but it cannot be dead, right? The radio can be in off mode or on mode. Can be a transmitter or a receiver, or it can be both in case of full duplex. So what we need to do is that we need to keep the controller asleep whenever we don't need to do any processing. And in other words, we need to minimize the idle mode. Because the active, I mean, since it's active, I mean, we have to keep it inactive because it's processing something, it's doing something, and we need it to do that. So active cannot be controlled. So we just need to minimize the idle periods and avoid this and keep it in a sleep mode most of the time. And then whenever we don't want to communicate anything, we need to keep the communication part turned off as much as possible, or also in a sleep mode. So for example, the sleep mode, it can be at different levels. So sleep mode can be multiple levels. You could be, just lying down, but you're not in a deep sleep, or you could be in a deep sleep. And depending on the level of sleep, the waking up will take probably more time, right? So if you are in a very deep sleep, waking up will take more time than, for example, if you are in a light sleep mode. So for example, the MSP 430, the microcontroller MSP 430 from Texas Instruments, this has 4 different sleep modes. The Atmel one has 6 different sleep modes. Okay, so so depending on the operation, or depending on the application, again, having more levels of sleep might be good or bad. Okay, because if you are in a very deep sleep mode, sometimes you cannot turn to a awake state unless you have to spend some amount of energy, which is overhead, and you will take time. So you will take time and energy. So depending on the application, you need to optimize these levels of sleep. This is part of circuit design. We have no control. This requires some circuit design in terms of VLSI or chip design. But so the microcontroller MSP 430 with 3 volt, the full operation can consume 1.2. So remember we talked about 11 microwatt as a sustainable level of power. Here, to just keep the MSP 430 working in fully operational mode, you have to sustain 1.2 milliwatts, which is more than 10 times the number that we have talked about before. The deepest sleep mode, which is the 4th level of sleep, consumes about 0.3 microwatts. Okay, and this requires that you have to be awakened through some hardware external interrupts. So any software interrupt cannot wake you up. We know the difference between software interrupt and hardware interrupt, right? So hardware interrupt, it's very low level. It's a circuit type of, have to click reset or something like this. So the Atmel with 6 levels of sleep mode, the operational mode draws 15 milliwatt in active mode, and 6 milliwatt in idle mode, and in sleep mode it's 75 microwatt. Okay, so by far, of course, this one draws or consumes more energy, the Atmel one, which means it's more this difference in terms of energy consumption might be because of 2 things. Sometimes the circuit design is more optimized in the MSP 430, okay, and that's why it consumes less amount of power. Or sometimes the circuit design is not the problem, but the problem is, or the issue is, the Atmel is more powerful in terms of processing. So this one has some complicated instruction set which requires complicated operation. That's why it consumes more power. Okay. So switching between modes, and I think we talked about this last time briefly. So we said that while you are in active mode, if you decide to switch to a sleep mode at time t1, okay, you will actually be in an actual full sleep mode after a time tau down. So tau down is the time that you take to switch from the active mode to the sleep mode. Okay, but that's good because once you decide to be in a sleep mode, whatever energy you are reducing, you are saving actually, right? The problem is here, if there is an event that happens at time t event, and you want to switch back to the active mode, then you have to wait for a time which is equal to t up or tau up until you reach to the active mode. During that time, all this energy is wasted because you did not utilize it in any way. And then you switch to the active mode, and only then you can do some processing. So what you need to do now is to make sure that the energy that you are saving is more than the energy that you are wasting. Otherwise, going from active to sleep mode is useless, right? So this is an easy example. So what is the condition on tau up and tau down that makes sure that going into an active, from active to sleep mode is feasible? So in that case, you need to calculate the energy saved and the energy wasted, and by making this greater than this, you can get the condition on tau up that allows you to decide whether you will go to sleep or not.
Yeah,
So
see, it's not only the energy that must be considered, also the time, because in a critical application,
yeah,
the time is...
the energy is a function of time. This energy is a function of time. So this P active is the level of power you need to keep yourself at in order to be fully operational, right? This is the level of power that you have to have in order to be in a sleep mode. So now the energy is power times the time, which basically is the energy is the area. This is the blue area and this is the red area. So basically, if we can calculate it easily, so this is the area is what? The area is half tau down times A. P active minus P sleep. This is the area of the rectangle, right? And then plus T event minus T1 minus tau down. Okay, this is this part, the blue part, times P active minus P sleep, right? So T event minus T1 minus tau down will give you this point minus this point, which is this line right here, okay, times P active minus P sleep will give you the area of this rectangle. So the area of this rectangle plus the area of this triangle should be more than tau up times P active minus P sleep. Right? Right? So this has to be, so this is the energy saved, and this is the energy wasted or overhead. Right? So time times the power gives you the energy. So from this, I mean, طبعا, of course, you can just cross all the power levels, so you can easily get, so tau down has to be less than the term on the other side. صح؟ صح؟ Too difficult?
No, maybe.
Maybe. Why are you not convinced? Yeah?
YTE minus T1 TD.
Minus T1 minus. This is minus, بس أنا أصلي sorry, the pen is not helping me. I'm trying to buy the new iPad with the new pen, the latest one, the iPad Pro, because it has a very nice pen with very sharp pen here, which allows me to write like very fine lines.
This term to get the area of rectangle in the middle.
Right.
So
the rectangle in the middle, yes.
It will be TE minus T down, not T1. Why T1?
So no. This point here, هنا, this point is T1 plus T down, right?
Okay.
Okay. So T event minus this part, which is T1 plus T down, gives you this line,
Okay.
right? Anyone not convinced? Okay, so that's an easy criteria based on which we say that if tau up is less than tau down plus 2, in other words, if we need to just complete this drawing, so tau up needs to be less than طبعا half here and half here, so tau down plus 2 TE minus T1 minus tau down. Or in other words, it's so this is TE minus T1 minus tau down. It's like this, right? So this is the condition on tau up. So if that condition is fulfilled, then I can go into sleep mode. Otherwise, going into sleep mode is not feasible. So that condition can be checked by the communication protocol, or by knowing T event. So if we know that we will not have any event happening until T event, then we make this quick check, and based on that we can decide whether we can go to deep sleep or not. Any questions? So this is an interesting part. So computation versus communication energy. So we can compute more and communicate less, or we can do the other way around. Okay, if we can compute more and reduce the communication, should we do that or not? And how much computation should we do in order to reduce the communication, whether a lot or a little bit or something like that? So we need to know, in terms of energy cost, what is the cost of computing something versus communicating something? Okay, so we need to know this this ratio. So to put them in perspective, this is a big motivation, by the way, for a lot of work that's been happening in sensor networks. So energy ratio, sending only one single bit through the transceiver versus computing one instruction is anywhere between 200 to 3,000, which means that sending one single bit is equivalent to running 3,000 lines of code. This is huge. So why is that? Because communication is very complicated. We probably don't think it's complicated, but the physical layer guys can tell you that. In physical layer, you have to do channel encoding, you have to do Viterbi, I don't know, like you have to do all of this. It's a very, very complicated process. So on average, to send one single bit, this is equivalent to running 3,000 lines of code by the microcontroller. This is a big motivation that tells us you should always try to compute more if you can communicate less. Okay?
Yes.
This is huge. This is a big conclusion now. So this is the big motivation for a field which is very specific to sensor networks, which is what we call in-network processing. So we should try to compute things within the network as much as possible, if that leads to the fact that we can reduce the amount of things that we communicate. Okay? So in-network processing itself has different forms, different mechanisms, different types, which we will discuss in a minute. Another important thing to reduce the energy consumption, as we said before, is by using the concept of multi-hub, right? So a source node needs to send the sink some information, so it can use enough power that allows it to go all the way to the sink. But this will consume certain amount of power from the source. Instead, if we can have some multi-hub, then the amount of power we need to send to this node is probably much, much less. And in fact, it is really proportional to the energy, the power that you need to send from here to here is actually proportional to the distance to the exponent of alpha. Alpha here is what we call the path loss exponent. And this path loss exponent tends to be greater than 2, which means that the energy decays, the energy or the power that we send from the source here decays by a rate of d to the power Alpha and alpha here is more than 2. The typical values for alpha is probably 3,
2 in
2.5, 3,
in
something like
rural
that.
and 4 in urban.
Actually, more than 2 in rural. In rural area, it's more than 2. 2, I think, only in vacuum. Vacuum, only in vacuum. But in rural areas, it's not less than 2.5. The typical value for city regions is maybe 4
3.7.
or 3.7. Okay, that's fine. Okay. Okay, so if we can reduce D, this means that we can potentially reduce the energy by more than half sometimes.
The source will collect the data from sync and then it will sense the results of collecting data to the
Yeah, well, this is what we call store and forward. So when the source sends to this node, this node can now do multiple things. It can say, okay, so you want to spend less energy and you rely on me. Okay, so I'm going to just amplify the signal a little bit and send it over. Just amplify the signal a little bit and send it. Okay? And then this one will do the same. Or you can say, I will decode or store, which means that I will convert this signal to a digital domain. Okay? And then I will store it into the buffer, and then I'll take the buffer and then convert it again into an analog signal and send it over. The advantage of this is that the decoding itself has certain probability of error. So if you decode and then forward, you enhance the bit error rate. You enhance the probability of error because you are decoding your convert. However, if you keep the signal in the analog domain and just amplify it, then the probability of error is amplify noise, exactly, because you amplify noise. I remember the guy when he first came to my house to set up the ADSL. So he said that I'll just set up one connection in downstairs. So I told him I need another connection upstairs. He said, no. You can get one of these range extenders. I told him, see, you're talking to a professor in communication. So do not tell me that I can just bring a range extender and it will work. And I was explaining to him, of course he did not get it, but I was explaining to him the fact that range extender will extend or will amplify the noise. Because range extender is good if you are in rural areas. You don't have any neighbors, you don't have anyone around you. But in cities, this is useless. I don't know how people they use this or they buy it in any way. It's useless unless you don't have neighbors around you. So because it basically uses amplifying forward, and amplifying forward amplifies the noise. So it doesn't make any difference. You're not actually gaining anything.
It's work in high signal to noise ratio.
Yeah, it works in high signal to noise ratio, and that happens only in rural areas. But I have many neighbors around me. Each one has, Wi-Fi signal and so on. So the range extender is going to amplify everything. My signal and his signal and his signal and his signal. So what gain did you get? So that's why store and forward tends to be more. Tends to have better performance. So store and forward in multi-hub, not the only possible solution. Even amplify and forward. So you can use some collaborative networking in the sense that you can use not decode and forward, but you can use code and forward. So you can merge the information and compress it. You can code it using some network coding techniques. You can aggregate it. You can do all sorts of things to make the information less. Okay? Because store and forward does not make the information less. It gets one packet and it outputs one packet. So it does not save the amount of information. It helps in delivering the information as is with higher probability of success, right? But it does not contribute to the fact that the information will be less. So there's a big difference, right? So in that case, these collaborative methods, they don't work on a per packet basis. They take group of packets and then they merge it, they aggregate it together using certain techniques. You can think of it as video. You get raw video, you get certain packets, but then you can use video encoding, right? To reduce the size of the video, right? You can do that in the network to reduce the amount of information you communicate. But then you can do that on multiple steps. You can do that recursively and in different steps at different sensors. You reduce every time you pass on a single sensor, the sensor fuses information from multiple nodes, and it reduces the amount of information it receives before it forwards it. Okay, an example of this we'll talk about. So for example, in multi-hop, just by just a simple example, this is the source, and this is the destination, and I have a node here, and I have another node here. Okay. So say that this distance is d, small d, and this distance is d. This is capital D. So in this is capital D minus small d. Okay. So if d equals d capital over 2, we want to calculate the amount of energy we saved. We want to calculate the amount of energy that we saved. So if d equals d over 2, so without relaying, the energy that we know that if we want to have a level of energy here, E output, okay, then the E1 here equals E output times C times D to the power alpha. Right? So in other words, E output divided by E1 is 1 over C times capital D to the power alpha. In other words, the signal itself loses the energy with a rate proportional to D to the power alpha. So if I want to have a level of energy here, E output, the level of E1 should be E output times D to the power alpha. Right? So this is without relay. So this is without having any node in between. Right? So let's see if we have relaying, then the amount of energy is actually the energy that the source needs to send to this node plus the energy that this node uses to send to the destination, right? which is, let's say this is E11. E11 is sending to, or let's see that this is relay مثلا. So E1 relay plus E relay, right? So E1 relay equals to C times D over 2 times alpha, right? Plus C times D over 2 alpha, all times E naught, right? صح? Assuming that it's D over 2, each one is D over 2, right?
But in this case, we neglect the receiving energy.
Yeah, we neglect the receiving energy, yes. Okay? The typical values for alpha, as we said, let's say it's 2, which is the best case scenario. This is in vacuum. So this is actually a 2C D over 2 to the power 2 E naught. So if alpha is 1, then we didn't do anything. But because of the fact that alpha is 2, this becomes D squared over 4, right? And this one is here, this is D to the power alpha. So this is E C D to the power 2, and this is C D to the power 2 over 2. Right? Because alpha is 4, as alpha is 2, so this is D squared over 4, and there's 2 here, so this is D squared over 2, which means that this power is double this power. Does anyone know why we selected a relay at D over 2?
Relation with the more relay.
Okay, so as a simple exercise, try it with D. Try it with D. And then we need to know what is the optimal D that makes the power minimum. So we can, for example, say, so this is the source, and this is the relay, and this is the destination. This is small d, and this is capital D, which means that this is D minus D. Okay? Get the E1 as a function of this, which is طبعا C D to the power alpha plus D minus D to the power alpha E. What is D that makes this energy minimum? Because we want to make it minimum, right? We want to make the energy minimum. Intuitively, what is D? يعني intuitively كده. Take a wild guess.
D over 2.
What is small d? هتطلع capital D over 2. How do you do that? How do you think we could do it? How can we make E1 minimum?
Differentiate.
Derivative, take the derivative. What is the, يعني to identify the minimum or maximum of any function, take the derivative. So take the derivative with respect to small d, and then we, at the minimum, this derivative should be should equal to a 0. Calculus, basic calculus. ماشي? So take the derivative and then equate this to 0, and then get the value of d. Prove that d is equal to d capital over 2. This should be very simple. Okay. And I apologize for the very bad handwriting, but so this pen is not helping me a lot. Just in this simple equation, you can easily prove that d small equals to d capital over 2.
And take alpha equal to
Alpha.
For any alpha.
Come on.
Doesn't matter. Okay. So for some design principles for the sensor networks, when it comes to processing the information and communicating it, the sensor nodes can be organized in a distributed way or centralized. So we can collect the information and pass all the information to the sync node, to the centralized node, and then the centralized node can then perform some kind of a centralized optimization or something, and then send back the results to the nodes. So this can be done to perform medium access control, or to perform routing, or to perform processing, or anything. So the problem with the centralized approaches is that they are usually not very scalable in sensor networks, in the sense that the number of sensor nodes might be very large. So to rely on the fact that you have to send all the information to the sync node in order to have some optimization done at the sync, and then send the result back to the nodes, this will not scale very well for large sensor networks. However, doing this medium access or routing in a totally distributed manner, it's also very challenging in many cases, particularly if you're talking about optimizing the power and synchronizing the duty cycles or the sleep periods and so on and so forth. So for example, if we assume that we have a star topology similar to Wi-Fi or similar to access point, and a number of sensors, then the access point can act as a synchronizer to all these access points. The access point can tell this sensor, you sleep, you wake up, you sleep, you wake up, because the access point will have a global picture, will have the overall picture. So it knows that this sensor wants to communicate to this sensor, and this sensor wants to communicate to this sensor. So it can synchronize easily when certain sensor can wake up or sleep or something like this. However, doing this in a totally centralized way will not be scalable for large networks, right? But also doing this in a totally distributed way may be very challenging, especially the issue of synchronizing duty cycles and for the purpose of optimizing the sleep times or optimizing the energy. So in other words, it's not clear whether distributed or centralized organization of these nodes achieves better energy efficiency. Okay, especially when we take the overhead of the protocols into consideration. It becomes very challenging or very tricky question to know whether the distributed or the centralized approaches will be more efficient, particularly when it comes to energy efficiency. And by energy efficiency here, we mean optimizing the sleep periods and the idle periods and so on and so forth. So an option that that's studied very commonly in sensor networks is the limited centralized, or what we call a clustered. So in that case, we divide the overall network into clusters and nominate local coordination or local controller within a group of sensors. This will help in many ways. This will help, on one hand, synchronize the duty cycles within this group of nodes. So in other words, so we have the network will be in a form of multiple clusters like this, and all of them, they communicate to the sink. This will help us that within each cluster we can do some synchronization for the duty cycles to optimize the sleep time within this cluster, and we can do that on a cluster to cluster basis. At the same time, we can be as scalable as we want to be, because the number of sensors in each cluster is going to be limited, right? We can have as many clusters as we want. Ideally, we would want to have one big cluster to simplify the problem of organizing the nodes or the duty cycles for energy efficiency. But that's not possible. So we can have limited number of sensors per cluster to perform this optimization locally, and then send some aggregate decisions to the sync node. This can also be very beneficial for the case of in-network processing. So the cluster itself can cooperate to aggregate the information or to do certain in-network processing within each cluster, send the aggregate information to the cluster head, and then the cluster head will send the aggregate information to the sync node. So the cluster topology usually has multiple benefits when it comes to addressing the trade-off between scalability, which is an issue for centralized, and organization when it comes to distributed. Okay? So this is a good, so the research issue here is how we form our clusters. Okay? How we nominate each cluster head. So these are research problems that have been addressed a lot. So what if these nodes are mobile? Can we have our clusters static, or we can have them dynamic? What if the nodes move? If this node moves to a certain area, should we make it belong to this cluster or this cluster? The cluster head nomination becomes an issue, whether in fixed or mobile. In fixed, we need to nominate a cluster head in such a way that the cost of sending to this cluster head is minimum, right? And at the same time, this cluster head should have some forward connectivity to the sync. The cluster head itself has extra functions compared to the other nodes. That will lead to the fact that the cluster head will drain its energy. So should we rotate the nomination of the cluster head across the clusters or make it fixed? Okay. So the issues are enormous for the case of cluster topology. There are so many. By the way, some of these techniques even apply for data centers. And okay. So in network processing, for wireless sensor network, we are expected to provide information, not necessarily original bits, as we discussed this issue before. So our job here is not just to transfer bits. Our job here is to answer questions, right? Our job for wireless sensor is to answer questions, not necessarily to send raw bits. Sometimes I'm deploying the sensor networks because I want to answer questions. I don't want to get like some raw bits and then store it. Okay? For example, I'm in patient sensor networks, I don't care about capturing the EEG, for example. I care about the fact that whether the patient has seizure or not. Right? I want you to answer this question for me. So this is the main objective. Okay? I'm not interested in the EEG itself. I'm not interested in the actual temperature. I'm interested in the average temperature in a specific location or in a very large area. Okay? So that motivates the fact that we can manipulate the data inside the network to answer or to provide the exact objective that you are looking for. Okay, so we can manipulate, we can process the raw information in intermediate nodes because we know that the ultimate objective is to answer a specific question. This is what we call in-network processing. So some examples, we can apply some aggregation techniques. So you want to send a temperature in one location, and I want to send a temperature in another location, and so on. Okay, so when a node gets the two temperatures, it just sends one message with the two temperatures. What is the saving here? Well, the saving is the protocol overhead. And instead of sending one number with all the protocol headers and stuff, I can send two numbers with the same protocol overhead. So this way, I can save the protocol overhead can be significant. Not only that, I can actually, while aggregating, I can instead of aggregation in terms of sending the two temperatures, I can send the summation of the temperature. If I want to get, for example, the average, I want to get the summation, and the sync node knows exactly how many nodes are deployed. So it just divides the summation by the number of nodes. It gets the average, right? So instead of sending two temperature, I can get the summation of those two temperatures. So this way, I can save. I can get the minimum easily. So when I receive two values, I can get the minimum value and send it over. So whenever a node receives the 2 or 3 or 4 values, it gets the minimum and send it. So this way, I know that for sure, I can guarantee that the only value that will propagate all the way to the sink is the minimum, or the maximum, or the average, or the sum, and so on. So instead of sending multiple measurements, I can always aggregate or merge this information into less amount of information. So this example illustrates that. So if I don't do any aggregation or merging or anything, then I have 1, 2, 3, 4, 5, 6 sensors. they are connected in such a way that this sensor is connected with this sensor, and this sensor is connected with this sensor. So this sensor is connected with two other sensors, right? So it receives one message from here, one message from here, and it has its own message. That makes it in total 3 messages will be sent across this link, right? So we're not doing any aggregation, we're not doing any merging in that case, right? So that makes it 1, 2, 6 in total, 6 messages. So we're just counting the number of messages on each link, right? So 1, 2, 5, 6, 7, 13. So here we have 13 messages. Okay? If we use aggregation or merging, we can simply say, okay, so I received 1 here, 1, 2, and I will send 1 here because I merged this with the one that I have, right? And I merged this with the one this, and I send only 1 message. So that makes it 1, 2, 3, 4, 5, 6. So here I have 6 messages. So what is the saving? The amount of saving. The amount of saving here is 7. 7 messages. So I saved 7 messages compared to the actual number of messages. So this is the amount of saving in terms of percentage, in terms of rate. So I saved more than 50%. Right? So I saved more than 50%. Just by this in this simple example. Okay? Okay, so in network processing can be as complicated as you can imagine. Sometimes in sensor networks, some sensors can cooperate to capture a video. They can do some collaborative signal processing or collaborative video processing. Because if you have one camera capturing the scene, then this camera will consume significant amount of energy, right? What you could do is that you can deploy 2 or 3 of those, and you can have one sensor capturing certain part of the scene. For example, you can have some sensor only detects the edges of a certain of the people in the scene. Another sensor to capture, for example, the texture. Okay. Another sensor to capture a background, something like this. And you collect all this information together, and then you can form the video. So you can fuse from multiple cameras and do some complicated image processing to form a certain video. You can do some temporal or spatial correlation. For example, you want to capture a video as very high quality or in very low resolution, or you want to only detect certain boundaries or the segments of the people in the scene or something like this. So you can vary this, you can adapt it temporally or spatially. So you can for example, you can say, like, you can merge multiple measurements, multiple historical measurements into one measurement. You can receive multiple measurements, like of temperature, of pressure, or something like this, and you can merge it temporally, which means like a history of measurements in a specific duration. You can take this history of measurements and then you can say, I will merge these into one big measurement, whether it's using aggregation, using any type of processing, encoding, whatever. So you can take, like, for example, a video frames, some video frames over time, right? And you can do some encoding. This is a very simple example. Take some video frames over time and then do encoding. Or you can do it spatially, which means that you can take the measurement from multiple sensors that are close to each other, okay, and fuse and collect this information and aggregate it based on knowing the fact that these sensors exist in a specific location, or they are close to each other. For example, you want to measure the temperature in certain locations. So you deploy many sensors, and then in this location you will get from 10 sensors, aggregate, get the average. From here, aggregate, get the average, and so on. Okay? So this is spatial correlation. So you know that these sensors exist in the same location, so you collect the measurements from them, you aggregate, and you send. Right? So this is the spatial correlation. Temporal correlation talks about the fact that you take a history of measurement and then you merge. Any questions here? Last thing is adaptive fidelity. Talks about the fact that using this concept of in-network processing, we can adapt the accuracy of the measurements based on certain application context. Okay? So we don't just process we don't just aggregate and do all kind of encoding and stuff in normal operation, but we can adapt this processing based on the application context. So for example, in a surveillance system, if I know that there's nothing happening in the scene, okay, but I want to capture the video, I can capture the video with a very low resolution because I know that there's nothing happening. But once you detect, and by detecting I mean sensors will detect themselves. Sensors locally detect that there is a specific something, there is some suspicious event happening. So all of a sudden, they all get, through collaboration, they all get informed and they raise the resolution. Because during this duration, I need to make sure that I capture all kinds of events that might happen, that might be happening. So this is called adaptive fidelity. So an in-network processing will not work consistently using one mode, but it adapts itself to the events that are happening. For example, I'm capturing EEG from a specific patient. So I can lower the sampling rate. I can, collect some simple features from the EEG signal. I can send that to the sync node. Okay? Then this means that I will do certain classification to figure out whether this patient has seizure or not, with a specific probability. Once I find that there is a probability that this person might be having an adverse event, then I will then inform the sensors, or the sensors maybe will detect that on their own, to say that, okay, we need to increase the sampling rate now, we need to process things locally to make sure that this person, whether he or she has seizure or not. So I will increase the sampling rate in that case, and I will have to do the processing to make sure whether this person is having any adverse event or not. So in that case, the in-network processing will have two different possibilities, one or two different modes, or maybe 3 or 4, depending on the fact that you are in normal operation, all is well, then you can use less sampling rate, you can capture information with less frequency and so on. Okay, once you know that there is an event, then you can increase the rate of message exchange. For example, an example of a temperature, when a temperature is in acceptable range, okay, I don't have to send the temperature every second, right? So only if the temperature becomes higher than certain event or certain threshold, or increases by an increment which is above, مثلا, let's say 5 degrees or 3 degrees or something, then and only then you can send the temperature with maybe high frequency, or higher number of messages can be exchanged between the sensors. So this way I can perform what they call adaptive fidelity, or I can adapt myself to the environment or to the application context. Okay, so we'll stop here, I think, right? So we'll stop.